Yeah, welcome to this session. Um, I'll share my screen now. Y- Um, are you guys able to see my screen? Hello?
So,
You are?
yeah, we can see it.
Yes. So yesterday we were discussing about single processing and multiprocessing. We stopped exactly here when we gave the example of symmetric and asymmetric multiprocessing architecture. Okay. So either way, when it comes to multiprocessing, it can cause a system to change its memory access model from uniform memory access that we call UMA to non-uniform memory access. Okay. We also need to understand what uniform memory access and non-uniform means. UMA is defined as the situation in which access to any RAM from the CPU takes the same amount of time. So there's uniformity in how long it takes to access any part of RAM memory. It doesn't matter the process that's trying to access this memory. There's uniformity in the amount of time that it takes to access that memory. In that case, we speak about uniform memory access. Okay. So from the CPU point of view, when it takes the exact same amount of time to access RAM, independently of the process at hand, we speak about uniform memory access. But on the other hand, with non-uniform, that will mean then non-uniform memory access will mean that it takes different times from the CPU to access the RAM memory. Okay, so some part of memory may take longer to access than other parts, creating a performance penalty. A performance penalty in terms of processing speed, of course. Operating systems can minimize the non-uniform memory access penalty. So one of the goals of designing an operating system would be to ensure performance. Of course, efficiency is a keyword we learned earlier on. So it's in that respect that a good operating system will be normally designed not to cancel non-uniform memory access because it's there, but to rather minimize the penalty that comes with. The penalty will be all the extra duration that certain processes from the CPU take to access certain parts of RAM memory. Okay, that's very important. So a recent trend in CPU design is to include multiple computing cores. Yeah, that is what I was mentioning earlier yesterday. I spoke about single processing. I spoke about multi-processing, but I also spoke about multi-core. I had referred to it as a multi-threading approach. But you can have more than one core in on a single CPU as a way for multiple computing. So multiple cores does not mean multiple CPU. There's a multiple CPUs. Multiple CPUs, which means multi-processing, is slightly different from multi-cores. When we've got multiple CPUs, we've got multiple full CPUs. When we've got multi cores, we've got multiple ALUs. I mean, the arithmetic and and logic units are many. We've got many cores within the same CPU. They can be more efficient than multiple chips with single cores. And having multi cores can be turned out to be more efficient than having multiple CPUs, meaning multi core can be more efficient than multi processing because on chip communication is faster than in between chip communication, definitely. Because when we have multi cores, we just improve the computing capability, but we still on the same chip, which means being on the same chip makes it easier to communicate among the different cores. The different cores will communicate faster among them than they would have communicated if they were on separate CPUs. Can you guys still hear me?
Yes, we can hear you.
Okay, you get that concept. When you've got multiple cores, you can communicate they can communicate among them much faster than if we had multiple cores on the single chip can communicate among them faster than if they were to be on different chips. Okay, because on a single chip, it's internal communication at the end of the day within the same CPU. Okay, which will turn out to be much faster. Okay, so that is multi-core as an alternative, therefore. Okay, uh, so in our coverage of multiprocessor systems throughout this text, unless we state otherwise, we generally use the more contemporary term, which is multi-core. Multi-core is more modern, and that is what we will be referring to by default. If we want to refer to any case of single processing or multiprocessing, we will say so. But in general, we'll be referring to multi-core by default. Okay. So a typical example of a multi-core is a dual core, meaning two cores, and it's displayed here in figure 1.7. As you can see, we've got two CPU cores, meaning two ALUs, which is the computing unit, and two cache memories, but coexisting on a single chip, unlike multiprocessing where that is shown earlier on, where it's different separate chips. Okay, that is very important to mention. Okay. Each one of them has its own register as well as its own local cache. Other designs might use shared cache or a combination of local and shared caches. So there is some variant within the set of multi-core computers as well, whereby you have three variants basically. In the one variant, each core, although sitting on the same chip, has its own registers and cache. That's the first variant. The second variant, they are sharing multiple cores, sharing the same cache and the same registers. And the third variant would be okay. Let me think about it. The third variant would be so either individual cache and the registers. Second variant, sharing sharing registers and cache. Sharing registers and cache among multiple cores. Okay, that is the second variant. The alternative is actually a combination of local and shared. Okay, yeah. So the third variant will be the case where you've got both shared cache and registers, and as well as non-shared. So you've got both. So certain registers dedicated for a specific core, and others shared between that core and the others. Okay, so those are the three variants of multi-cores you can also have. Okay, very important to mention that. So finally, we also look at what we call blade savers. These are relatively recent development in which multiple processors board. So we've got multiple processors, it's multiprocessing. We've got multiple IOs, and networking boards are placed in the same chassis. So a blade saver is just a couple of computers in one box, basically, because everything is separate. Multiple processor boards, multiple input-output boards, multiple network boards, but all of them in one chassis or one case. Okay. The difference between these and traditional multiprocessor systems, so they are not multiprocessor systems because the, I mean, sorry, yeah, the CPUs are not living on the same computer necessarily. They're just in the same box. Okay. The difference is that each blade processor board boots independently and runs its own operating system. Yeah. So the operating system is actually the key thing that makes a difference here. In a multi-processing system, although we've got multiple CPUs, they are coordinated, or their actions are coordinated by a single operating system. In a blade saver, we've got multiple CPUs. All they share is the same house, but they run independently, and each has its own operating system, which means each boots up separately. Very important. Okay. So some blade savers boards are multiprocessors as well. So within the blade saver, it's not impossible to have a multiprocessor computer as part of that blade saver. So as much as we've got multiple computers under the same case, you can have one of those computers being a multiprocessor computer, meaning with more than one CPU running under the same operating system. So this brings in an extra dimension in terms of what we consider to be multiprocessor. Multiprocessor, it's multiple CPUs coexisting under the same hardware, but not the same hardware, sorry, under the same computer hardware. Okay, but running also or coordinated from a single operating system. Unlike with blade servers, where you might have multiple computers coexisting under the same casing, not necessarily same computer hardware. First difference. Secondly, each one running an independent operating system. So that is very important. Thirdly, we've got what we call clustered systems. And when it comes to clustered systems, these are quite popular systems in computer systems, and they are multiprocessor systems. Sorry, they are multiprocessor systems, meaning they've got multiple processors, but multiprocessor system clustered in a clustered system. When we speak about cluster, we mean a group of elements sharing some common fate, basically, or common task, or in computing it could be common task or common mission or common function. So in networking, cluster will be a couple of nodes together cooperating, exchanging packet, etc. So if we have multiprocessor systems under a cluster system, meaning networked together to talk to each other and share resources, okay, so at the end of the day, we've got multiple CPUs all together because they are, we can view them as having multiple CPUs all together, although they are networked. So it's separate computers. It's separate computers, each with a CPU that are networked, but through the network they form a cluster, and through that cluster they can share ability to process, meaning processing ability, memory, etc. Okay. So clustered systems differ from multiprocessor systems. Okay, in that they are composed of two or more individual systems. It's individual systems, that is the key difference, or nodes, also known as nodes. You can't speak about clustering without speaking about nodes. So hence the term nodes. Joined together by means of what? By means of a network, of course. Such systems are considered loosely coupled. That's another way to refer to them. They are loosely coupled because they are coupled, they can share processing speed, they can share memory, but they are also at the same time independent. But because all this sharing only happens through a network from one computer to another. Each node may be a single processor system, as we mentioned, or it could be multi-core system. But at the end of the day, as long as it can communicate in a network, in a cluster of other computers, are you guys still able to see my screen?
Yes.
Yeah, as long as they can communicate in a network of, with other computers through a network, they are classified as clustered systems. Okay. We should note that the definition of clustered is not concrete. Many commercial packages wrestle to define a clustered system and why one form is better than the other. Okay, so yes, it can be confusing because especially now that almost any computing systems are networked. When you go to an office place, different computers there's always at least a common drive that is being shared among computers where people can share files, etc. There's at least a common printer and so on. So in general, computers tend to be clustered. Hence, to make the distinction between a clustered system and a non-clustered system can be blurry in the age of networking and edge computing that we live in nowadays. Okay. All right, so my computer is almost up. I'll shift to it once it is. Okay. So each node may be having a single processor. That's important. So, but it's not only single processor, it can also be multi-core. Okay. Clustering is usually used to provide high availability service. And that makes sense. High availability or reliable service would be provided by a clustered system because there is the principle of interdependability, meaning if one system was to be down, the other one can take over, can detect that first of all, and takes over its task. Okay. So that will be the main benefit of a cluster system. Clustering can be structured asymmetrically or symmetrically once more. In symmetric clustering, one machine is in hot standby mode. So that is the machine that keeps sort of surveilling the other ones. Okay. While the others run the applications. So there's in a sorry asymmetric clustering, we have some form of a client server type of configuration whereby one machine is more like the server. It's in high standby mode, and it doesn't do any processing. All the others do processing, and once they're done, they give the processing data to it, and that can be pulled from there. Similarly, to the client server type of architecture. Okay, the host standby host machine does nothing but monitor the active servers. So it's done that is monitoring the others and see if they're down or up. If that server fails, the host standby host becomes the active server. So it takes over from the one that fails. With, of course, the objective to still provide high availability service, as we mentioned. Okay. But now, in the case, yes, go ahead.
So what happens if two or more fails, say?
Okay. Yeah, that's a very good question. Yeah. Normally, in every computer system where there is a handover, as we call it, there is always an order of priority, which should be clearly defined in advance. If more than one computer fails, what should normally happen is that it should take up the task of one of the computer. Is that okay? Over the other. So then there's a problem. Like there's no perfect system. There will need to be some level of priority definition in that case. Okay.
So with that level of priority, let's say the other one fails and then the other one fails. The first one that fails has the least priority, and then the second one that fails has the highest priority.
It
What
should
will
take
happen?
over. Yeah, it should take over, switch to the high priority one.
Also, it will just switch to the high priority and leave the low priority one.
Yes. And when I speak about priority, and you'll see this when we get to shared resources, it's not necessarily just priority defined in terms of computer systems that are in the cluster. No, priority can be as deeply defined as at task level. So it could be processes. So what I'm trying to say is that priority can also be defined in terms of or configured in terms of task. Maybe, for example, I'll give a typical example of mini computers because you are computer engineering. Let's say we've got a water meter, smart water meter, for example. It's running on a microcontroller and so on. There is sensing of water flow and there is transmission of data, for example, via IoT or through the network, right? Of how much water we've sensed and so on. Now, which one? Naturally, it will be more priority to sense how much water is gone through. So, highest priority will be given to the water meter measurement. You get the point? Rather than the communication. Okay, but there could be a scenario where, if we go task wise, there could be a scenario whereby the task of uploading maybe every midnight a packet, which shows the consumption for that day, takes over measurement. So you could stop measurement just for uploading the daily consumption, for example. So the point I'm trying to make is that priority can be, in this case, defined in terms of which computer has got more priority, and that can be based on the type of task that computer performs, or it could even be defined in terms of the task, a specific task that could come from either computer, especially in the case where all computers perform the same task. So it could be defined in terms of the task that could come from either computer that would have a higher priority than the other. Make sense? Are you there?
Yes, I'm here. It makes sense.
Okay. Now the alternative is symmetric clustering. In symmetric clustering, now you have both computers playing the role of server and client at the same time. So each one monitors another, if it's 2 or 3. So everybody detects whenever the other person is down and so on, and can take over. Which means it manages its own applications. All the computers in the network do have applications or tasks to execute, but they also monitor what's happening with the others. Because now, what will happen is that if they're not busy with their own applications, they can always squeeze in activities from the other that might be done at that moment. And since a cluster is made up of, and then the problem of what if both fail is still there, of course. As I mentioned, there's no perfect solution. It's just an extra, we just going, with cluster system, we are just going extra precaution in terms of handling possible faults, because faults happen in computer systems all the time. Okay, but there's still a limit, because in the end, all can die in both symmetric or asymmetric clustering. Now, so because of the ability, because of the fact that computers in a clustered system are networked and can cooperate in terms of how they share resources, from processing resources, meaning their CPUs are shared to a certain extent, from memory resources, that they end up providing what we call a high performance computing environment. Okay. That is very important to note, because otherwise there wouldn't be any benefit in clustering computers. That will be one of the key benefits. Okay, so now that will be one of the key benefits in that sense. Now, the application must have been written specifically to take advantage of the cluster. So it doesn't help to network computers, but without them running a specific application. And this will be normally some form of network application. Without them having that network application that allows them to cooperate. So okay, I may have a lot of tasks and send some of the tasks to another computer to help me process them. Once it receives it, it processes them and sends me back the result. In the meantime, I might be processing some other task. When I get the feedback from the other computer, I combine the two results to provide a global result. And then I will have executed, if I split my task into 2, then I will have executed that specific overall task in half the time, for example. This is what we call parallel computing, actually. That's what we call parallelization. And this is parallel computing, which is a field on its own in computer engineering and computer science that someone can even specialize in and become an expert in. And it's very critical because parallel computing is very high in demand. And certain operating systems, what we studied here is that certain operating systems are much easier to use in parallel computing than others. So there is a concept or an aspect about parallelization, that one must consider while designing an operating system. Okay. Other forms of clusters include parallel clusters and clustering over a wide area network. Okay. Parallel clusters will be computers already in a cluster. Then you also have on top of that another cluster. Okay. Does it make sense? So it's a cluster of clusters, if I can put it like that. Okay. But you can also have clusters over a wide area. Sorry about that. Most of the times when we speak about a cluster, we are mostly referring to a local network. But you could have a cluster over a cluster one way, but you can also have a cluster over a wide area network. We're talking about your typical clustering of computers across maybe the entire Route 10, for example. Okay, so this has to do mostly with the geographical extent of the cluster you are talking about in this case. Okay, because most of times when we speak about cluster, by default, it's a set of computers more or less in the same geographical location. Okay, so parallel clusters allow multiple hosts to access the same data on shared storage. Okay, so those are common drives and so on. because most operating systems lack support for simultaneous data access by multiple hosts, parallel clusters usually require the use of special version of software and special releases of application. Okay, before I even go in the Oracle example, I'll give you a typical example. If you take modern Windows, let's say 10, we can consider that modern enough. You would go on a specific, you'll easily go on your, let's say, folder, how do you call it, folder window, and you can type an IP address in the bar as a path, in the path bar, and that can lead you through the network to a remote server somewhere. And if you've got a long enough path to that to that computer server, you can go all the way inside a folder on another computer. You get the point? Okay, but that was not necessarily the case in older Windows version. In older Windows versions, you either had to map a drive, and then only you can access it. In older Windows computers, before even the mapping of a drive, you probably needed another extra application to sort of team view into that specific other remote computer, or so you have to team viewer into it also. Or there used to be something called, I can't remember the name, that will access you remote control thing, remote control application. We don't need the remote control application necessarily nowadays, unless you really want to control the other computer. But if it's for file sharing, for example, you can just, and I'm shifting now to the computer, you can basically go to the, like in the case of Windows, you can go to, let me share my computer screen on the other side. Sorry. Stop sharing here. Okay. Yeah. So this is what I'm talking about. I could go to a folder, I mean, a directory like this. From this directory, using the path bar, I could access a remote server, for example, but from Windows without having to have an extra application. So I could say, I'll just take one of the servers I know I have access to, and I could say enter. And from there, I could be taken immediately to the server. Does that make sense? So already when I'm here, I'm already on another computer. You get the point. And this is all handled from the operating system point of view. So cluster systems, the handling of cluster systems is actually also, should also form part of the operating system design. Needs to be considered, in other terms, as part of the operating system design. Okay. Are you guys still able to see my screen? I want some feedback, please.
Yes, sir.
Okay. So I just want to go to the page at which we were. We are slow. Actually, we need to move. Especially because this part is more of a revision. So we'll go a bit faster. Okay, it's page 17. Yeah. So we just, now you understand what clustered systems are, and how important it is to have them in considered as we design an operating system. Okay. Now we also have what we call distributed lock manager. But before I go there, I just want to speak a bit about the Oracle example. Oracle RIA Application Cluster is a version of Oracle's database that has been designed to run on a parallel cluster. So as you know very well, you can have Oracle database applications. So now there's a specific one that has been designed specifically to cater for parallel clustering. So each machine runs Oracle, and the layer of software tracks access to the shared disk. Because database is all about storage, So we're talking about a shared disk, and we have therefore a piece of software which could be even part of the operating system that manages access by multiple computers to the same disk. So this is Oracle applications, multiple sessions of Oracle applications on multiple computer systems, making use of the same storage, same disk at the end of the day. This is very common even in the accounting space. In the past, you would install, let's say, Pastel on every computer in an organization that needs it. Nowadays, they can just all access it through the server. Okay, so the operating systems must enable parallelization. You might have the best parallelization tools, but if the operating system you are using does not allow for that, or does not cater for it in a more efficient ways, you won't either get the experience or won't get a good experience. Yeah, so that is very important to mention. Okay. To provide this shared access, when we speak about shared access, we know we're talking about attributes of the operating system, because it's, at the end of the day, it's the operating system that manages the sharing of any resources. The system must also supply access control and locking to ensure the non-conflict operations occur. So yeah, at an operating system point of view, and when we study memory organization, we'll touch on this again in much more details. At an operating system point of view, there must be some authentication method to avoid conflict, and to at least keep track of who did what modification on the shared disk. Okay, so that function of managing authentication of users on a shared resource is what we know as distributed lock manager, DLM. So now the question is DLM normally part of an operating system or not? Anyone can answer that? No one? Anyone? Are you guys there? Can you hear me?
Yes, we can, sir.
It will be part of the operating system, because at the end of the day, anything to do with resource management must be a part of the operating system, in one way or the other. So now, depending on which resource is being managed, you get different names for different things. So, like you get a file management system for managing files. You get, like in this case, a distributed lock manager for managing access to shared memory, etc. Okay. So now, that will be part of a cluster technology, and a cluster technology is changing rapidly. Some cluster products support dozens of systems in a cluster. So the number of nodes that can be in a cluster, which is what we call scalability, is also a very important metric to assess the performance of a cluster. Of a cluster technology. The more nodes a cluster technology can handle, the better, of course. Okay. Many of these improvements, so some cluster products support dozens of systems, as well as cluster nodes that are separated by miles. They could be, so it's two things. It's coverage, meaning how far apart the nodes are, as well as number of nodes, which we call scalability. So now there are many improvements that are made possible in terms of enabling this cluster technology. And this is thanks to what we call storage area networks. Storage area networks, these storage area networks allow many systems to attach to a pool of storage. So there's couple of, so storage area networks simply means a network of storage. It's not necessarily a network of computers, but it's just a network of memories. Memory storage that are networked together, meaning they're seen as one, although scattered in geographically. So it's like having a hard disk here and another hard disk 10 kilometers away. But if the one is full, data can be shifted to the other and so on, because they are networked and they can collaborate. And that's exactly what is explained there. If the host fails, then the others can take over. And that's very critical, especially in database systems, especially when we need what we call redundancy. I'm sure you guys have been doing database management systems. Have you done a database module so far? So, no. Yeah. So this is the case where you've got multiple computers accessing a database that is hosted by a server somewhere. And each one has got an IP address. It's accessing this storage area network through an IP address. Okay. Now, we have what we call multi-programming, and we're getting there. So, multi-user, there's multi-user systems, there's one single-user systems. There's multi-processing system, there's single processing systems, and multi-core systems. Then we also have what we call multi-programming systems and single programming systems. In a multi-programming system, you can have multiple programs running on the same computer system. And the operating system for such a system will be different, obviously, from the operating system running on a system that only execute one type of job, meaning one type of program. Okay. So now let's look at what, but we'll discuss multi-programming in much more details. But let's look now at operating system structure. What is the structure of operating systems? Now that we have discussed basic computer system organization, we have an idea of the different types of computer systems we might encounter. We've done the organization, we've also looked at the architecture. We are ready to talk about operating systems now. An operating system provides the environment within which programs are executed. Okay, provides the environment for execution of programs, because at the end of the day, computing is about execution of instructions, and these instructions are programs. Internally, operating systems vary greatly in their makeup, since they are organized along many different lines. There are, however, many commonalities which we consider in this section. One of the most important aspects of operating system is the ability to multi-program. So an operating system must be capable to handle more than one application at the same time. Otherwise, it's not an operating system. Otherwise, there's no use for it. It's because we have an operating system that we are able to open Word and Excel at the same time, for example, on the same computer. So a single program cannot, in general, keep either the CPU or the IOs busy at all times. And the operating system is managing that. The CPU is being accessed by multiple programs at the same time. I mean, not at the same time, but one at a time. Single users frequently have multiple programs running. That the Word, Excel, Outlook scenario I explained earlier on. And that is what we call multi-programming. So multi-programming increases CPU utilization by organizing jobs. So now, it organizes jobs, so the different programs access the CPU in terms of different job requests, and the CPU programs or schedules through the operating system. Of course, the operating system schedules for the CPU different tasks related to the different programs, and it executes them in such a way that at the user point of view, you seemingly have the same experience. As you feel as if when Word is running at the same time as Excel, for example. Okay. And this, but when you look in time, the CPU normally execute one single job at a time. Okay, so the operating system keeps several jobs in memory simultaneously. Since in general, main memory is too small to accommodate all jobs, the jobs are kept initially on the disk first, in what we know as the job pool. This pool consists of all processes residing on the disk, awaiting allocation of main memory. So the memory, the main memory, which is RAM. When we speak about main memory, you know it's RAM, and that's the purpose of the early subsections it was to make sure that we are familiar with the terms. So when I say main memory, you know it RAM. So RAM is not too much often, maybe 4 gig, but you might have a lot of tasks or jobs for the CPU. So what will happen is some will be kept there, the ones that need to be executed almost immediately, but others will be stored on permanent memory, meaning on ROM, under a section that is reserved for that we call job pool. The pool consists of all processes residing on a disk awaiting allocation by the RAM memory. The set of jobs in memory can be a subset of the jobs kept in the job pool. So the jobs that are already in RAM might be subset or sub jobs or tasks under the same job that is still kept in the job pool. So what that means is that it might happen that at the same time some parts or tasks of a specific computer job are already in the main memory, while some others are still residing in the job pool. So the operating system has the task to pick and begin the execution of one job, of one of the jobs in memory, one at a time. So pick, every word is important here. Pick and start the execution. First of all, pick, because what does it use to pick? It uses a certain number of criteria. What are these criteria based on? These criteria are based on a certain performance, expected performance in terms of, which could vary greatly depending on which operating system we're talking about. From mobile operating systems to microcontroller operating systems from microcontroller to mobile all the way to computer to server to mainframe. So the selection, and we'll learn the different techniques to select the task or processes one after the other or one over the other. Okay. Then the second part, that the job that the operating system does is to begin the execution. So it's done that also kickstart the execution, inspire the CPU to execute a specific task after it has picked it, or of course. Okay. So eventually the job may vary to wait for some task, may have to wait for some task. Yeah, it may happen that the job that is being selected has to wait for some task, or such as an IO operation. Maybe there's something coming through a network port, an email or something, and a job might wait for that to conclude before it carries on. Okay. Now, in a non-multi-programmed system, the CPU would sit idle. Yes, will sit idle in such a case, because while it's waiting for the next job, it would be doing nothing. But in a multi-program system, the operating system simply will switch to and execute another job in between. So during the execution of a job, different tasks might be executed, and you might get to a task that requires, let's say, data to come through an IO controller into the computer system, meaning at that moment the CPU is not busy because the controller is handling the acquisition of that data. In a multi-programmed operating system, what will happen is that the operating system would be able to execute some task of another job quickly, while the IO controller and the data acquisition is finishing. Okay, but in a non-multi-programmed operating system software, what will happen then is that while we're collecting data through an IO, for example, or any other activity, the CPU will be idle, which is a wastage of resource in that case. Okay, because it does affect the overall completion of all tasks. Okay, so when that job needs to wait, the CPU switches to another job and so on. Okay, eventually the first job finishes waiting and gets the CPU back because it's done collecting maybe data from a USB or something like that. Then it can get back the attention of the CPU. But in the meantime, instead of going idle, we will have used the CPU for other tasks. As long as at least one job needs to execute, the CPU is never idle. So with a multi-programmed operating system, the CPU will never be idle for as long as there are tasks to be executed, whether those tasks are from the same job or from different jobs, because it's capable to execute tasks from another job within dead zones or idle or supposedly be idle zones of the execution of the other. Okay, that's very important. So this idea is common in other life situations. That's just an analogy. A lawyer does not work for one client at a time, for example. While one case is waiting to go to trial or have papers typed, the lawyer can work on another case. That's just a typical example to explain this in a much more understandable way. Multi-program systems provide an environment in which the various system resources, meaning your CPU, your memory, your peripheral devices, are utilized effectively, but they do not provide for user interaction with the computer system. So all of that is handled in the background. In a multi-program system, is handled in the background, and these resources are being shared, and the management of that sharing is solely a responsibility of the operating system. Now, how then one would think, how would these resources be shared? There are many approaches to that, and these are the different techniques now when designing the operating system to cater for that. We've got what we call time sharing, which is known as multitasking. So that's a logical extension of multi-programming. So it's one program at a time, but it's multiple programs not running at the same time, but one at a time. Okay. In time sharing systems, the CPU executes multiple jobs by switching among them, but the switches occur so frequently that the user can interact with each program while it's running. So you might have two programs, they're not running at the same time like it will be the case in a multi-programmed operating system, but in a time sharing, they're running, the jobs of these two programs are running one after the other, but that is happening it's just happening too fast that you can't notice, and you have the impression that they are happening at the same time. So time sharing requires an interactive computer system, okay, which provides direct communication between the user and the system. There need to be a direct communication between the user and the system. The user gives instruction to the operating system. Let's say he clicks and select, let's say, save a file. Okay. So the instructions goes normally through the application program first. If there's any API, it goes through it, and after the API, it filters down to the operating system, and you know how from the operating system it reaches the corresponding hardware. So now the user will give that instruction without, directly using an input device such as a keyboard, for example, or a mouse or a touchpad, or a touch screen in the case of a mobile scenario, and waits for immediate result on an output device. So you click on a touch screen, you expect something to appear on the screen, for example, to use the case of a phone, and the mobile operating system in this case must handle that. So now, accordingly, the response time should be short. Of course, that's the when you speak about efficiency, that will be the criteria, and it should be less than 1 second. 1 second is used like anytime below 1 second in this case is considered to be real time, meaning almost considered to be zero time, meaning didn't consume any response time. A time-shared operating system allows many users to share the computer simultaneously. Okay, since each action or command in a time-shared system tends to be short, only a little CPU time is needed for each, as the system switches rapidly from one user to the next. So there shouldn't be very long tasks for a time-sharing performance to be good. Because the CPU should be able to do a task, get done with it, move on to the next one, etc. So each user on his side is given the impression that the entire computer system is dedicated to his use, although that's not the truth. Okay, it's being shared by many users, but the tasks or requests from the different users are broken into subtasks, short ones, and they're executed one at a time so rapidly that the users wouldn't feel it. Each user has at least one separate program in memory. A program loaded into memory and executing is called a process. That's a very important keyword when it comes to operating system as a subject. You can't speak about operating system if you don't speak about processes. So we speak about a process the moment a program is available in memory and has been loaded from memory to execute. So it's under execution and it's being loaded from memory. When a process executes, it typically executes for only a short time before it either finishes or need to perform input-output activities. Input-output may be interactive, that is, output goes to the display for the user, and the input comes from a user keyboard, mouse, or other devices. Now, since interactive I/O typically runs at people's speed, it may take a long time to complete. Input, for example, may be bounded by users' typing speed, yeah, because if it's a keyboard and it's not typing itself, how fast you can type will determine how fast data can come in. Okay, it may be bounded by the typing speed, seven characters per second, for example, etc. Okay. Time sharing and multi-programming require that several jobs be kept simultaneously in memory. You need to store the different jobs before you start executing them one by one. If several jobs are ready to be brought into memory, meaning into RAM, and if there's not enough room for all of them, then the system must choose among them. So there must be a selection. And when we say the system chooses among them, that is the task of the operating system once more. So this decision of choosing which jobs come in is what we call job scheduling. And that job scheduling is definitely an operating system task. And it's discussed in chapter 6. When the operating system selects a job from the job pool, it loads that job into memory for execution. When we say memory here, we're talking about RAM. So to load it into RAM for execution. Having several programs in memory at the same time requires some form of memory management. Exactly. Memory management, very important. We cover that in chapter 8 and 9. We have to study that. In addition, if several jobs are ready to run at the same time, the system must choose which job will run first. And that is CPU scheduling. So there's job scheduling, which has to do with deciding which job runs first. Memory management, which has to do with how you organize the programs or the jobs as they are loaded from memory. And CPU scheduling has to do with the decision to decide which job must run first if they were to attempt to run it simultaneously or at the same time. And that we also study in chapter 6. Finally, running multiple jobs concurrently requires that their ability to affect one another be limited in all phases of the operating system. Very important. Let's say two tasks use a shared memory. So this will be a printer, for example, in a computer. Whenever you want to print something, you send it to a specific memory, it's loaded there, and the printer reads it from there and prints it. But if another person also has access to the same printer, the mechanisms must be put in place in such a way that two different people can access that shared memory with no conflict. A typical conflict is one system sends a file for printing, but the other one deletes it, for example, before it's printed. Then you get a printer will get an error and will get stuck in that error because there will be no file for it to print. Just to give some sort of conflict that needs to be managed also by the operating system. Okay, that's very important. Now, in a time-sharing system, the operating system must ensure reasonable response time. This goal is sometimes accomplished through what we call swapping, whereby processes are swapped in and out of memory to the disk. A more common method for ensuring reasonable response time is what we call virtual memory, and we will discuss virtual memory in details, of course. Okay, so we make use of virtual memory to improve on swapping activities, okay, or swapping efficiency. and that is covered in chapter 9. We'll definitely study that. The main advantage of virtual memory scheme is that it enables users to run programs that are larger than the actual physical memory. So we've got 2 gig on chip, but we can actually run programs that are bigger than that 2 gig, for example, because we can make use of virtual memory. Yeah, it's an abstraction level in that sense. Further, it abstracts main memory into large, so it makes RAM look bigger than it actually is. Okay, uniform array of storage separating logical memory is viewed by user from physical memory. Okay, so it's sort of an extension of physical memory, but it's virtual because there's no actual hardware catering for it. This arrangement frees programmers from concern over memory storage limitation. So it sort of solves memory storage limitation. But we'll get into much more details when we study chapter 9. A time-sharing system must also provide a file system. Of course, file system is a very integral part of operating system. The file system resides on a collection of disks. Hence, disk management must be provided too. Okay. In addition, a time-sharing system provides a mechanism for protecting resources from inappropriate use, and that will be the security aspect of operating system design. To ensure orderly execution, the system must provide mechanisms for job synchronization and communication. So that processes and threads, how they are synchronized, and that is discussed in chapter 5. And it may ensure that jobs do not get stuck in a deadlock. Yeah, very important. Forever waiting for another job to complete, for example. All of that is processes and their management. I think I'll stop here for today. Thank you for attending. Next time we'll speak about operating system operations, but 1.4 clearly labels or outlines the rest of the subject content that we'll focus on. Okay. Thank you.
So how many chapters in total are we going to do?
Yeah. Okay. Okay. Let me answer that quickly. I'll tell you under a normal semester and under a short semester like this. There's a difference. But what we do is we work with the normal semester and we see how far we get. But there are some critical chapters that we must do. Okay, so 1, of course, we are busy with it. 2, we'll do basically. When it comes to process management, yes, we need to do processes, thread, synchronization, and CPU scheduling. Yes, we need to do those. But now we might, like for example, do 3 and 5, because a process is almost the same as a thread. There will be small chapters in any case, but if we have to skip one, we'll do processes, for example, only, and not do threads. Okay, then 6 and 7 are very critical, because that way the problematic is discussed, scheduling as well as deadlocks. Okay, then as part of memory, we need to do main and virtual, but most important is virtual. Of course, we may skip main. Yeah, that's it. Protection and all of that will be nice, but we won't have time to do that. I think I forgot file management. Sorry. Yeah, we need to do file system management. Absolutely. So you should see it more in terms of parts rather than chapters, because these chapters are not very long actually. For example, this one starts at 131 and ends at, no, sorry, where did it start again? It starts at 503, it ends at 543, so that's 40 pages in general. But as I mentioned, I'll also get slides, which will be nice summaries instead of the entire content. Is that okay?
So say, will the slides be safe for us to study using them during exam?
Yes, but if there is a specifics, when it comes to test and assessment, I'll give you specific scopes or sections to cover. Because what I'm really after is understanding, not necessarily memorization. Makes sense? And we also have a shorter semester, so I'll prioritize among these chapters. Is that okay?
Yes, it makes sense.
Okay, thank you. Okay, so I'll see you tomorrow morning.